Hello, calculus students. Welcome to your first whiteboard screencast of the semester. There will be 30 or 40 more of these. So if you have any comments on how I could make them more useful to you, the student, the most important person in the screencast, let me know. I'm open to suggestion. I'm learning how to do this at the same time as you guys are learning calculus. So the first topic that we're going to really talk about is the topic of slope, secant, and tangent. And I think we're going to start in reverse and first talk about tangent. So let's get in the thing here. So what is this tangent line? We're going to investigate the tangent line. What is it? Well, this is a tricky definition. Let's say we have some curve like a parabola. That's my best parabola. And if we kind of know from geometry class what a tangent line looks like. So let's just try to draw a tangent line that goes like that. Okay, so what are the properties of this thing? Well, it just touches. Tangent, the root of that word means to touch, and there it touches. It doesn't really cross, just at one point. So sure, that's a tangent line. But what if our curve looks a little different? What if our curve looks like this? Say the curve kind of starts like this, then kind of goes down, and then flattens out like that, some sort of a cubed root or something. And what if I wanted the tangent line right here? Well, to do that, I'd kind of have to draw it up here. And it goes through there. Well, it definitely touches, but it might cross. So we can't really cut the cross, but at least it's only at one point, right? So we got that going for us. All right, well, what if we have a curve, say like a cubic curve? The one above it is a cubed root, so I'm trying to draw a nice, smooth, cubic-looking thing here. And say I want the tangent at this point, there. And so I'd have to draw this, kind of goes out like that. That looks pretty good, and it goes down like that. Well, we touch at one point, kind of like we did here. We didn't cross it, but it crosses down here. Now, I think everybody in here would agree tangent line, tangent line, tangent line, but what really makes it the tangent line? I think what the definition we have to pick is it's a straight line and it's the same point, and most importantly, what do you think? What characteristic does it have? Same slope at that point. And that's really kind of what we're after. We're trying to figure out, to draw this tangent line, we know what the point we're after is, but we need the slope. So how do we get the slope? That's the big question. This has been it was a really big question for a lot of mathematicians from the year, early 1400s to the mid 1700s that mathematicians were working on this. All right, so slope. That's no problem, right? We know all about slope. We learned that in ninth grade. How about slope is, remember this one, rise over run. All right, we can do that. Or we can use some kind of fancy mathematical terminology and say it's delta y over delta x, right? The delta, Greek letter that means change. It's a triangle, equilateral triangle, but it's the Greek letter capital delta. Well, if we wanted to calculate delta y, we'd say it's y2 minus y1 over x2 minus x1. So the change in y, like how far is it from y2 down to y1? Well, that was the rise. And how far is it from x2 to x1? Well, that was the run, delta y over delta x. That's the slope. So we should be able to find the slope of a curve, no problem. I'm going to draw just kind of a basic one here. The first curve that many of us learned about in school was the parabola. The parabola is nice. And we'll say that this is y equals x squared there. And let's say I want we'll do it in the same colors we used before. I want the slope right there. I need rise over run. Well, that means I need 2 points. I need a y2 and an x2 and a y1 and an x1. So let's call this point 1 here. And then, well, we need a second point, so let's just put it over here. And I can sketch a line in there. Now, drawing straight lines with this thing is a trick, at least with this software package. And so I can draw a line in like that. And that's not too good, but we can see that, well, the slope isn't quite a match. So slope is close. But not great. Yeah, it doesn't quite match down there. All right, fine. So we could calculate the slope of the blue line. It's the same general slope as the curve at this point, but it's not exactly the right thing. So what do we do? Well, to get a little better idea of what's going on, we're going to look at a different example. So what do we do? In the different example, we're going to look at a different problem. Now, normally I ride my bike to school, but I think you'll understand in a little bit why my bike ride to school is not such a good example for the point I'm trying to make. So I'm going to kind of exaggerate a little bit and say that I drive. I much prefer to ride my bike, but driving provides a better illustration of this thing. Now it turns out that if I plot, this is distance here on this axis, that I live about 12 miles from school. I live on the near west side. And it takes me about 30 minutes to get to school. So if I put time over here, and this is about 30 minutes. And that's how long it takes me. Well, if I were to drive kind of during the morning commute, which would drive me insane. But in 30 minutes, I would get to school. Right? But what does that look like? Well, first I have to kind of leave my neighborhood. And let's do this in a little different color. Well, my car is black, but it's got gray interior, whatever, dark blue. It'd be nice if I had a dark blue car. So we, you know, I'm kind of, for the first little part of my drive, the first few minutes, I'm not making very good progress because I'm getting through my neighborhood. And so it's kind of slow. But then I can speed up on one particular street. And then I have to go around this bend. There's often some traffic, and it slows me down. So now the time is ticking by here, and I'm not making much distance. And then I get on a busier street, and I really make a lot of progress, and then I kind of get to UW campus, and it stops, and it goes, and it stops, and it goes, and it stops. And then finally I get on like Packers Avenue, and I really make good progress, and then I get close to the parking lot, and it slows down, and finally I get to school. So this is what my commute to school looks like if I were to plot distance versus time. Right? Sometimes I'm making a lot of distance with a little bit of time. Other times I'm not making any distance. I'm stuck at a red light on campus waiting for pedestrians. Pedestrians doing the right thing, but they're not allowing me to drive. So the obvious question, if I just told you 30 minutes to go 12 miles, is how fast am I going? Right? Well, we know from experience that speed equals distance over time, right? We know that. Equals 12 miles in 30 minutes. And so that equals, let's see, 12, 6 over 15, and 2 over 5. So that's 0. 2/5 is 0.4 miles per minute. Now that doesn't make a ton of sense. We don't often talk about miles per minute. So I could also write this as 12 miles over 0.5 hours, right? Because 30 minutes, this is 30 minutes. And this is miles up here. So 30 minutes is half an hour, and so that equals 12 divided by 0.5. Now that's more reasonable. 24 miles per hour, right? Now, does it make sense that I only drive 24 miles per hour on my way to school? No. But it definitely took me 30 minutes, it definitely went 12 miles, so what does this 24 really mean? So the 24 miles per hour is my average speed. Very important there, average speed. That's not a question mark, that's a fact. But what if I want to look at one little section of my drive here? Okay, I really kind of want to know how fast am I going when I'm on Campus Drive here. Let's zoom in on Campus Drive. We'll put a little box around that. We'll zoom in on this section of my drive. And we'll kind of head over here with that. So this is the zoomed in section as Dressler is driving on Campus Drive, which is kind of a 4-lane divided thoroughfare going through Madison. And it looks like I'm going pretty fast here for a while. I'll do this in the same color. I'm going pretty fast here. I'm making a lot of distance, not much time. And then there's a stop site right by the mechanical engineering building where I have to stop. All right. So, and I want to know what my speed is right here. So what is my speed here? So how fast am I going on Campus Drive? Well, if my speed is distance divided by time, or essentially the slope. So speed is slope. So I need a rise over a run, right? So I could pick another point. I need 2 points to make this work. So I can make another point over here, right? And I could draw this line that goes through these 2 points. That one a little better. But you see that didn't really work. My slopes are definitely not the same there. So, I mean, I'm still at least kind of moving towards campus here, but my slopes don't match. Now I know the obvious thing you're saying, well, Dressler, you picked 2 stupid points. Okay, let's pick a better point. Let's pick a point that's a little bit closer here. Right now we'll do this. We'll draw a line through those 2 points. Well, still not great. I mean, it's better. The orange is better than the red. But what if I picked another point and I picked that point right here? So now all of a sudden, I've got something that is pretty close. So my red point here, what happened here? My speed, right, really included time at stoplight. Right, that's why I picked red. Right, in this, the orange one I picked here, this is better but still not a great approximation as I move my second point closer to where the point I'm interested in. Finally, for the green one, this is pretty good. Now, this may seem really, really obvious to you, that of course, if I take 2 points really close together, for instance, the middle of Campus Drive and then a spot 100 meters later, something like that, then I'm going to get a much better approximation than if I take 2 points that are far apart. Okay, and I hope that's obvious to you, and you think I just wasted 10 minutes of your time, but I want you to convince yourself that we need 2 points that are close together to make this work. All right, let's revisit the parabola. So I'll go back to our boring math colors here. Revisit the parabola. And so I'm going to draw a pretty big axis here and a pretty big axis here, because we need a lot of room to do that. That axis didn't turn out so hot. But this is going to be x, and this is going to be y. And my parabola looks something like that. So this is f of x equals x squared, like that. And my point that I'm interested in, I'll stick with the same kind of color scheme, or at least I'll try. The light blue point is down here. And so right below that is x. There is the x. I want to know the slope at this point. And so if I go horizontally across here like this, this must be f of x, right? I plug x in and I get f of x. But I need 2 points, so I'm going to pick another point. Much like I did a couple pages ago, we haven't made much progress. So there we go. And I'm going to bring this down here. And you remember from algebra class, college algebra, maybe even in high school, we learned that oftentimes x distances are kind of any change in x. Sometimes we call that h. Right? And then so if I go over here like this, this is f of, it's not f of x, it's f of x plus h, right? Because this point down here, I'll do it in red, is x plus h. Okay, well, if I were to draw a straight line, and this is going to be challenging, between those 2 points, like that, I could calculate some slope between those two. And it would be the rise over the run. So let's try that. Y2, whoop, don't want that, not y squared. A lot of people do that. You got to make sure it's a subscript. Y2 minus y1 over x2 minus x1 equals, what would that be? So y2 is f of x plus h, and the first y is f of x, right? So the difference, my rise is f of x plus h minus f of x, and my run is just x plus h minus x. Well, that's nice. So if I kind of simplify this, the bottom simplifies a little bit. It's f of x plus h minus f of x divided by x, and those cancel out. So that's h. Great. Why did we bother doing all this? I realized, from the car example earlier, that if I move this second point closer, Or in other words, the smaller my h is, the better it's going to be. So let's maybe draw a better example in here. Let's do it in green, because green is better than red. And let's draw a second point in here. And so this will be a better x plus h. And so this is a better h. And then over here is a better f of x plus h. All right, so now if I draw a line in here, that goes like that, and that goes like that. Well, that's certainly better. I mean, it's still not great. The green line is still not exactly the slope of my parabola, but it's better. So how can I make it even better yet? Oh, yeah, I know how I could do it. If smaller is better, the best value of h would be what? 0. So if we stick a 0 in there for h, we could stick a 0 in this formula, we'd be golden. Ooh. But we have a problem here. We can't. We can't use h equals 0. Why? Because that gives us division by 0. All right. And division by 0 is the greatest sin one could commit in mathematics. Well, sometimes when you get stuck and you realize, this isn't going to work out so well, you just you charge ahead anyway. We know that f of x is x squared, so f of x plus h would be, so I'm going to say that, save a little time here, m is slope is going to be x plus h squared, just charging ahead here, minus f of x, which is just x squared, all divided by h. Well, x plus h squared, I remember my binomial squared is x squared plus 2xh plus h squared minus x squared, all divided by h. Whew, boy, it's getting uglier, but maybe we can do some canceling. So I got my red pen here. Okay, x squared cancels with x squared. And now I have 2xh. Let's write the next step here. Equals 2xh plus h squared all over h. And then, wait a minute here. There's an h in everything, so I can cancel that out. I can cancel that out with that. So what is this? My slope actually ends up being, that's interesting. Everything canceled. The h on the bottom cancels, so I don't really have that problem anymore. 2x plus h. But the best value of h is 0, so I can even get rid of that. H equals 0. So my slope, when I've done this, equals 2x. So my slope really kind of pans out here. So if I said this is, if I said x equals 1 over here, where's my cursor? There. If I said x equals 1, then the slope would be 2. If x equals 3, the slope would be 6. And that seems reasonable. The farther out I go on a parabola, the steeper it gets. And the slope is always twice what the x value is. So, by just charging ahead and doing some algebra, this problem cleaned up a little bit so that I could cancel out my problem. Now, I did gloss over this a little bit. You can't always just cancel out problems. We'll talk more about this in the next couple of days. But for the meantime, we've come up with a pretty slick solution. So let's do another example of this, similar to what is going to be in your homework. Let's say that I have example. I'm going to say y equals x cubed minus 2x squared plus 5. And I want to find the slope. I'm going to do two things. Let's see, make easy numbers here, x equals 1. And then, let's see, estimate with point x equals 3. All right, so what are our 2 points? M equals y2 minus y1 over x2 minus x1. Y2, if I plug a 3 into here, that's 27 minus, let's see, 9, 18, that's 9 plus 1, 14. And so 14 minus, if I plug a 1 in there, 1 minus 2 is negative 1, 4. Over, well, 3 minus 1 is just 2, equals 10 over 2 equals 5. All right, well, I don't know if that's a reasonable answer or not, so let's maybe make a sketch. It's always good to make a sketch. We'll draw this kind of like this guy here, and then we'll draw this guy down here, and let's draw the point 1, draw the point 2, draw the point 3, 1, 2, 3, and I know if I plug a 0 in, I'll get a 5. So let's just make this a 5 up here. Now notice when I sketch these, my scales don't match exactly right. That's okay. We're just trying to get the gist of this here. And then at x equals 1, it's 4. So we got to go down. Let's draw it in a different color. My curve will be orange, because I like orange. We got a point there. At 1, it's going to be 4, so it's going to be there. And then at 2, I don't know, but at 3 I know it's going to be 14. So it's going to be way up here somewhere. So this curve is going to look something, and I know cubic equations in general look like this. So it's going to go like that, and then it's going to go down here. And my first take on it, I'll do it in red, was that if I use the points from here, that little thing keeps popping up, to here, I get a straight line that looks like that. Now this is, so m equals 5. Not so good. Right. I mean, it looks to me like my line is sloping down here, and my red line, my estimate is going up. So this is just not a good estimation. So let's take the this other approach where I'm going to use a really small value of h. I got to do a little algebra. So I need to do x plus h cubed, which could be a hassle, minus 2 times x plus h squared plus 5 minus this whole thing, which is going to be x cubed minus 2x squared plus 5 all over h, right? So x plus h cubed, I do happen to remember this, remember Pascal's triangle and the binomial cubed. I think this gives us x cubed plus, and the coefficient becomes 3, x squared h plus 3x h squared plus h cubed. Remember the coefficients for a cubic go 1, 3, 3, 1. And then minus, let's see, x plus h squared is x squared plus 2xh plus h squared, so that becomes multiplied by 2. 2x squared plus, we gotta subtract this whole thing, 4x squared, x h, better erase that, that was pretty sloppy, 4xh plus 2h squared, and then we have to add the 5. Right? And then from that we subtract this thing, which is just x cubed minus 2x squared plus 5. And that whole thing is going to be over h. Wow, this is an algebra fest, isn't it? You're taking calculus here, not algebra, so let's clean this up. We have an x cubed, and then we subtract an x cubed down here, so these go away for sure. We have a x squared h. Any other x squared h's? No. xh squareds? Nope. How about an h cubed? No other h cubeds. A minus 2x squared, and then a minus 2x squared. Oh, that's nice, because those cancel out. And then a plus 5, and then a minus a plus 5, so those cancel out. That's pretty nice. So is that everything? I think it is. So this cleans up a lot. So m equals 3, let's write it up here, 3x squared h plus 3x h squared plus h cubed minus this thing here, so minus a 4xh, and then minus a 2h squared, and then the 5's go, everything else is gone. Holy cow. And all this goes over h still. Now, what's cool is that the only thing left up here are things with h in it, so I can cancel out this h on the bottom. This h cancels out with that h, it cancels out one of those, it cancels out one of those, it cancels out all of that one, and it cancels out one of those. Alright, so what are we left with at the end of the day here? M equals 3x squared, and then this h, wait, what's the best value of h? Oh yeah, h is best when it goes all the way down to 0. So 3x times 0, that goes away. Let's see, h0 squared is 0, minus 4, this h canceled out, so that just becomes minus 4x. And 2 times 0 is 0, the h is all canceled. So my final slope is this. Now this is a pretty important step. It's not my final step, but it's pretty important, so I give this a dotted box. Alright, and at x equal to 1, which is what I was originally interested in, m equals, well, 3 times 1 squared is 1, 3, minus 4 times 1, 3 minus 4 is negative 1. So that's our final answer. Let's put a box around that guy there. Alright, so our slope, and let's do that in green. Put a check mark by that. Slope is negative 1. Sure enough, that's more believable. If I draw a line through there, m equals negative 1. Perfect. Alright, so there you go. We have now investigated, that a secant line is an okay approximation to this. Why am I an eraser here? A secant line is an okay approximation to the slope of a curve, but the tangent line is really the best. The tangent line has the same slope. The only way we can do that is to use this imaginary h and shrink h down until h becomes 0. We can avoid dividing by 0 because all these h's cancel out. All right, and that's the gist of it. Please give worksheet 2.1 a crack, and we can talk about this more in class.